In this video, we're going to talk about the atmosphere of the Earth. So what is the atmosphere of the Earth? The atmosphere is a mixture of gases. Now, those gases aren't the same everywhere. As you go higher up, the gases will get lighter and thinner. As you go closer to the Earth's surface, the gases will get thicker and the pressure will increase. Now, the atmosphere doesn't just allow us to breathe, it also insulates the Earth. So the atmosphere surrounds the Earth, and during the nighttime, it keeps heat in. Now you might be wondering, why is it harder to breathe at higher altitudes? Well, as you go up, there are literally less atoms in the atmosphere surrounding you. And there's less atoms, including oxygen. And you need oxygen to breathe. So it's harder to breathe because less oxygen atoms are making it into your lungs at higher altitudes. Now, what's in Earth's atmosphere? Well, it's a mixture of gases, so obviously there are a lot of gases. The first and most important is probably nitrogen. It's been there forever. There's also oxygen, some water vapor in the troposphere, argon, carbon dioxide, and other trace elements. Now, these elements can vary based on what layer you're in. For example, the troposphere is the only layer that really contains any appreciable amount of water vapor. But on average, over the whole atmosphere, there's less water vapor because not every layer has it. Now, you could look at this on a pie chart. Maybe you like that instead of text. You can see nitrogen makes up most of the atmosphere, then oxygen, and then argon, and then all these trace elements only make up less than 1% of the whole atmosphere. So there's carbon dioxide, neon, helium, methane, krypton, and hydrogen as well. Now, Earth's atmosphere has not remained the same over time. Let's take a look at the most one, nitrogen. So nitrogen is mostly inert, so you would think it would just sit there and not do anything, but it does react. Most importantly, it reacts via fixation by bacteria. And because bacteria take nitrogen from the air and put it in the ground, some of that nitrogen is lost to the ground. It gets trapped underground. So the amount of nitrogen over Earth's history has actually been reduced in the atmosphere. It's been trapped into the ground. It used to have twice as much nitrogen in the air as it does now. Now, carbon dioxide also changes over time, obviously. We'll take a look at that a little bit later. And some other trace elements, argon and krypton, really kind of remain the same because they're so unreactive, being noble gases, they kind of just sit around. Hydrogen and helium would sit around, especially for helium, except they're lost to space. So every day, every hour, every second, kilograms of hydrogen and helium are lost to space. Now, what about oxygen? Kind of important, we need to breathe it, but oxygen also has changed over time. It's been lower, it's been higher, it's been non-existent. So a few billion years ago, greater than 2 billion years ago, there was no oxygen on Earth. About 2 billion years ago, bacteria started making it through photosynthesis. And then about 450 million years ago, oxygen levels really took off and remained relatively stable, above 20%. So you can see here on the graph, about 400 million years ago, oxygen levels were about 17-18%. And then once land plants started really taking off, oxygen levels were higher. Now they have dipped lower than current levels in the past, that is certainly possible. But for the most part, in the last 400 million years ago, oxygen levels range from about 22 to about 27%. Now currently they're about 21%, which seems low on average for the last 400 million years. And that certainly is the case. It changes based on climate, plate tectonics, and other factors. What about some other gases? Well, water vapor is one that we've talked about, and water vapor certainly does change over time. In the past, it made up a huge component of Earth's atmosphere. Currently, it makes up just a tiny fraction, and it just depends. It depends on a lot of factors, including the temperature of the Earth, the water cycle, and plate tectonics as well. Argon and krypton are in there as well. Methane and ammonia used to make up a significant portion of Earth's atmosphere, but they tend to react, especially with oxygen. And so methane and ammonia are relatively minor constituents of today's current atmosphere. They still do exist, but they tend to disappear pretty quickly, especially with an oxygenated atmosphere. Now, what happened to Earth's atmosphere? So I mentioned a lot of the atmosphere of Earth has gone away. And that's true. If you look at Venus, Venus may be what Earth used to look like, at least atmospherically. So Venus has about 90 atmospheres of pressure. what about Earth? Well, we actually think that Earth used to have a very similar amount of pressure in its early history, something like 55 to 80 times more atmosphere in the past than it had now. What happened? Most of that atmosphere got trapped in the rocks, and most of that they think was CO2. So something like 55 to 70 atmospheres of carbon dioxide may be trapped in the crust and in the mantle of Earth. How does it get trapped? Well, carbon dioxide, it could get trapped in coral reefs and carbonate deposits. It could also get trapped in oxides and metals, so bonding to things like iron, which is probably the major one. It can bond to aluminum, nickel, a whole bunch of other metals. And as those metals react with carbon dioxide, they get trapped in the Earth's crust, usually the oceanic crust, and subducted back down into the mantle. Now, a lot of that mantle carbon dioxide is trapped forever. It's never coming back. Some of it does get released by volcanoes, but as you can see, a whole lot of it, 55 to 70 atmospheres, is trapped in the rocks. And that will continue to be the case. Now, I also mentioned earlier that nitrogen is fixated as well. Yeah, the same thing happens. Nitrogen is fixated into soil. Some of those rocks and soils get subducted into Earth's mantle, and that's where they stay. Now, there are a couple layers in the atmosphere. If you need to know them, here they are right here. There's the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere, not pictured here. They are separated into upper and lower layers. So the lower layers are the troposphere and the stratosphere. That's where we live, for the troposphere. And the troposphere and the stratosphere actually contain about 99% of the mass of Earth's atmospheres. So even though down here it doesn't look like it contains that much of the atmosphere, it's actually most of it. The upper layers, the meso, thermo, and exosphere, contain only about 1% of all air. Now, what is the most important layers? Probably the troposphere, because that's where we live. That's where all life on Earth lives in as well. The stratosphere, you may have been there as well. Some commercial aircraft may fly at the bottom of the stratosphere, depending. But most of them stay in the troposphere for most flights. Now, finally, pressure. Earlier I mentioned pressure decreases as you go higher up, and that is true. As you can see on this diagram, at higher altitudes there are less molecules of air around to exert pressure. Lower down, closer to the Earth's surface, there are more molecules of air to exert pressure. So what happens? The molecules of air push against surfaces when there is more of them. When there's less of them, they have less of a push. Now you may see molecules, or you may see pressure represented in these terms down here. So we have bar, or atmospheres. So you can see Earth's pressure at sea level as 1.01 bar, or 1.01 atmospheres, ATM. You might also see kilopascals, so 101.135 kilopascals, or psi as 14.7 psi at sea level pressure. Now, obviously, all of these numbers will drop as you go higher above sea level, and they will increase as you go lower below sea level if you went somewhere like Death Valley. So that's it for today's video on Earth's atmosphere.